When defining acids and bases, we have used the Arrhenius definition and the Bronsted-Lowry definition. All in all, we think that acids are species that can release protons, or they're proton donors. Bases are species that accept protons. A very even more general definition of acids and bases can be done by, instead of using protons, using electrons. So the Lewis definition of acids and bases defines an acid like an electron acceptor and defines a base like an electron donor. Notice that this is not that far from the Bronsted-Lowry. It's just the Bronsted-Lowry definition. Like if you think of HCl, the moment that we call that a Bronsted-Lowry acid because it's a proton donor. What happens when the proton gets released? Well, it accepts, the chloride will accept that extra electron. So you can think of a Lewis acid as an electron acceptor. Okay, but that makes the whole definition more general because it pretty much can define a lot of the chemistry. You may have learned that in organic chemistry as electrophile, the electrophile, and the nucleophile. The electrophile will accept the electron pair, and the nucleophile will be the one giving that electron pair. Okay, notice that to identify acids, the Lewis acids and Lewis bases, most of the times what we need to do is to draw Lewis structures and identify what atom or what species may be deficient in electrons and therefore being a Lewis acid. Okay, an acid again will be an electron pair acceptor, also known in organic chemistry as electrophile, or a Lewis base will be an electron pair donor, or also known in organic chemistry as a nucleophile. For example, you may have seen the attack on carbonyls by alcohols or any other lone pair. That's because you can draw a Lewis structure in which the carbonyl has a positive charge on the carbon. This carbon is deficient in electrons. This will benefit the attack of a nucleophile into the carbonic carbonyl. Okay. So the exercise is as following. Can you draw the products of this Lewis base plus a Lewis acid? It may not be straightforward to identify which one is the Lewis acid and the Lewis base, so let's make sure we can draw the Lewis structure. Okay, notice that borons typically do not follow the octet rule. They are deficient in electrons. Therefore, this means that it will benefit from a nucleophile or a Lewis base. So you will have boron now. Okay, and of course this is a partial donation, but then yeah, this would be negative and this is positive. You can draw other Lewis structures maybe, but this is definitely a donation of electrons from one to another. Okay, and so notice that while HF was in water acts like an acid, a Bronsted acid, in terms of a Lewis definition, it can act also like a base, like a Lewis base. Okay, the same for if you have calcium hydroxide, and this may not make a lot of sense here if you draw it like that because it's an ionic compound, but notice that I'm gonna see one. If you draw it like that, you will see, well, the sulfur is very happy. Why should it want to get any more electrons? But notice that we can also draw it a little bit more like that. Therefore, now this sulfur is really deficient in electrons, so this will benefit from a Lewis donation. Okay. So on and so forth. It's may not be straightforward, but the moment you can draw a Lewis structure in which the species is deficient in electrons, that will be a good candidate for a Lewis base. Likewise, if you have potassium iodide, and here well, this one seems to be very happy, but notice that you can always donate one. Let me see. Right? You can always donate this one here and have the so-called triiodide ion. Okay, so this would be your overall triiodide ion. Let's make sure that we have the right number of electrons. This is 7. This is 1, 2, 3, 4, 5, 6, 7, 8. That's the extra one. And 7. Okay? So that would be another Lewis acid reaction with a Lewis base. Okay. A more common reaction that mixes both definitions is when you have what we call highly charged metals, and that will be the case for aluminum 3 plus or iron 3 plus. You will see that aluminum 3 plus in water, the aluminum manages to surround itself with 6 water is tightly bound in here. Okay, aluminum 3 plus is so tightly bound, and again aluminum acts like a Lewis acid. It accepts so much electrons from water that one of the, if you want to put it like that, one of these hydrogens debilitates its bond so that it gets released. So you can think of a Lewis acid like a cation that is acid because it ends up releasing protons. So careful, because you will end up seeing aluminum 3 plus as a substance in solution that releases H+. How can that be? Well, when you have a highly charged metal, it can weaken some of these bonds so that it gets released in water. The same goes for iron. So if you have, should be able to draw 6 around them. It's called an octahedron. Okay. These may release some protons, typically just one, okay, in which one of the waters loses one proton and gets released. So therefore, it's not only in this case a Lewis acid, it's also a Bronsted acid because it ends up releasing a proton in solution.